Alright, so I realized that maybe I went a little too fast in explaining this thing. So one comment I'd like to make is that here what we used to obtain this inequality. So this is an inequality that holds for any p in this interval, right? So this is just an inequality between like real numbers. And to see why this holds, note that this simplifies to 4p squared minus 4p plus 1 bigger than or equal to 0 if you simplify this, and this is just equivalent to 2p minus 1 whole squared bigger than or equal to 0, and the square of any real number is bigger than or equal to 0, so that's why this holds. There's also an obvious way of seeing this as what is called the arithmetic mean geometric mean inequality, for those of you guys who know this. Okay, but the point I'd like to make is that this is an inequality that holds for any real number between 0 and 1. In fact, it also holds outside because of this proof, but we only care about 0 and 1. Okay, so we have this Bernoulli, and like we saw last time, the mean squared error of this estimator is given by this quantity, and and that is at most 1 divided by 4n. Right, so now what does this tell us about confidence intervals, right? So once we have a bound on the mean squared error, okay, so there are two things to notice here. So there is a bound on the mean squared error, and other thing is that we actually know this bound, right? So we actually know this given n. Okay, and so this is the reason I ended up having to use this inequality. Okay, so because if I wanted to work with this value, I cannot, because I don't know what the value of p. I mean, p is what we want to find in the first place. Okay, so this is why I had a bound on this which is somehow independent of p. Okay, and that bound was 1 by 4n. Okay, and yeah, so and that's a value that we actually know. Okay, so now we can apply the corollary that we saw before, right? So the corollary basically said that if you have an estimator for theta and if you have a mean squared error of gamma, then the lower confidence interval and upper confidence interval are given like this, right? So let's fix some value for alpha. Let's fix alpha equals 0.04 as we did before. Then what this gives us is that L is equal to the estimate, which we'll write st. Okay, so the estimate is just x1 is the empirical mean. So the lower confidence interval, the lower estimate for the confidence interval is t minus square root of 1 by 4n gamma divided by alpha, right? So 0.04, and this one, if you simplify this, so this is equal to t minus root of 5n by 4. Oh no, sorry. So 1 divided by 0.04 is like 25 by 4n. Okay, so that's the lower estimate, and the r is equal to t plus root of 25 by 4. Okay, so what does this mean, right? So suppose, so what this means is that if I have a given n, okay, then my empirical mean, so the intuitive meaning of this is that if I'm estimating, say we want to estimate parameter p of a Bernoulli, Okay, of a Bernoulli distribution is what I mean, using samples, using n samples. Okay, then but what we said is that the empirical mean, then P actually belongs to this interval t minus root of 25 by 4n and t plus root of 25 by 4n with probability at least 0.96. Okay, and this comes from the fact that we set alpha equals 0.04. Okay, so there's a pretty high probability of lying within this interval. Okay, where t is the empirical mean. Okay, or the natural estimate for. Okay, so but this, okay, so what is now the length of this interval, right? So this length, we would ideally want the length of this interval to be somewhat small, right? So ideally we want a pretty short interval, because your goal might be to say that, oh, okay, so P belongs to t minus zero point 0.1 and t plus maybe 0.1 is even not good enough for you, maybe 0.01 or something. Okay, so you may want something like this with a high probability, right? Right, so this is a typical goal, right? So if we have a Bernoulli, so there's one parameter P. We know that P lies between 0 and 1. So you would like an estimate where maybe the error is somewhat small, because P lies in this interval 0, 1. And let's say P is equal to zero point 0.4 or something, then you would like to say that, okay, it is it's 0.39 plus minus 0.02 or some small error like this, right? So that's the kind of estimate that we are thinking about. Okay, and what this is telling us is a way to obtain this, right? So one way of viewing these confidence intervals is as saying that, suppose I want an error of let me replace this by epsilon so that we have a general formula. Okay, so ideally we want something like this with high probability, say 96%. Okay, if we want to have something like this, then we must choose n. For this we must choose n such that root of 25 by 4n is less than epsilon. Okay, because if it is, so if this is strictly smaller than epsilon, then it's even better, right? So this is what we must have, and this is equivalent to saying that n is more than 25 by 4 epsilon square. Okay, so another way of interpreting this bound that we have is that if we want error in an estimation error of epsilon with probability 96%, then the number of samples that we have, okay, which is like the number of points that you've seen from this distribution, must be more than 25 by 4 epsilon squared. Okay, and this, note that it makes intuitive sense, right? So this captures the intuition that more samples give better estimates. right? So this, for example, I mean, you see this unfortunately in the news all the time these days, which is that because we don't have too many tests for this coronavirus, we end up with an inaccurate values for various probabilities, right? So you'd like to estimate, for example, things like what is the probability that a random person in the population is affected, for example, right? So that tells you what fraction of the population is affected. Now, if you were to test a whole bunch of random people at random, then you would be able to estimate this quantity to a pretty high accuracy. But we don't have that many tests, and that's one of the problems, right? So this notion of confidence intervals actually it appears a lot in many applications, and especially in when dealing with like medical situations. Okay, so that's something to note. Okay, and this formalizes this intuition that more samples yield better estimates, okay, and with high confidence. Okay. Now suppose I ask you, okay, what if I don't like the probability 96%? What if I want probability of 99%? Okay. Now that's very simple. How do you do it? You say that, okay, probability 99% is like setting alpha equals 0.01 instead of 0.04. Okay. And then I plug that value into this estimator. Okay, so instead of 0.04 I put in 0.01, and then if you work it out, you will get that you get something like, instead of 25 you get 100 over there. Okay, so that's the kind of dependence that you get. Note that this is actually not great. Okay, one thing I would like to say that numerically, if we want, this bound is not great. Okay, so this is more of a comment. Bound obtained via Chebyshev is not great. Okay, what do I mean by that? If we want epsilon equals, let's say 0.01, which is a reasonable accuracy to want, right? Like if you have some parameter between 0 and 1, you may want to estimate it with an error of 0.01, okay, 1% error or something. Okay, so then we want n to be more than 25 divided by 4 times 0.01 whole square, right? So this turns out to be something like 25 by 4 times 10,000. Okay, and this, if you compute it, this is 25 by 4. Let's just say it's like 6.25, right? So this is something like 62,500. Okay, so if you have 62,500 samples, then you can be 96% confident that you've estimated your p to a value that is to an error of 0.01. Okay, so that's how you interpret confidence bounds in this case. All right, so this is this is one way of obtaining confidence intervals, and it's a fairly general way, as you can see, because if you are as long as you have a distribution for which you have some bound on the mean squared error, okay, so if you have an estimator with some bound on the mean squared error, then you end up with a with like confidence intervals of this kind, and these are not terrible if you think about them, because these are not great, but they are also not terrible. Okay, so that's something to keep in mind, especially if the confidence value that you need is not too high, then these bounds are actually somewhat tight. Okay, so let's say I want a confidence of 75%, then there's not then you don't really get anything better even if you use fancier bounds. Okay, so that said, let me start off with what we will see in the next lecture. So we'll do a very basic version of this. So the next example is, so this is what we said in the beginning that we would do. Okay, so we would end up with confidence intervals for the Gaussian, okay, for the mean of a Gaussian when you know the variance. Okay, so let's get to that. Okay, so now the quantity, now let's say we have samples x1, x2 to xn drawn from, so this is a standard symbol like I said, from a Gaussian with mean mu and variance sigma squared. Okay, and assumption for now is that sigma squared is known. We want to estimate mu. Okay, so in this case, okay, so we can actually use Chebyshev's inequality as well. Okay, so okay, but before we jump there, so the first thing, right, so we want to estimate mu. Now how do we estimate it? We use an estimator. So this one we use, let's say we use the empirical estimator. Okay, this is the empirical mean again. Okay, and let's say I want confidence intervals for this estimator t. Okay, what does the Chebyshev form? What does Chebyshev tell you? It says that we need a bound on the mean squared error of this estimator. And this is a calculation that we did last time. That's basically the expected value of t minus mu whole squared. And this, it turns out in this case to be exactly equal to sigma squared by n. Okay, so it turns out. And this is by computation that we did actually last class. But maybe you won't see it directly. But this is a good computational exercise if you want it. Okay, but this is optional if you just trust me that this holds. Okay, so so this is a bound on the mean squared error, and now we assume that we know this sigma. Okay, so now Chebyshev will directly give you some bounds, right? So suppose we want confidence of alpha. Okay, alpha confidence intervals. That's to use the term that we used before. Then we can do what we said before. You can set L equals the estimator minus square root of the mean squared error, which is sigma squared by n divided by alpha. You can set R equals t plus root of sigma squared by n divided by alpha. Okay, so this is something you can do. Okay, but and this is true, right? So now with L being this and R being this value, you can be confident that mu lies between, so we can be, so the probability that mu lies between LR is bigger than or equal to 1 minus alpha. Okay, but for the Gaussian and for a bunch of other distributions like this, it turns out that you can get much better bounds. Okay, bounds when alpha is if we care about very small alpha. Okay, So these bounds, like I was hinting at before, if you want alpha equals, I don't know, 1/4 or some, which is like 0.25 or something, these bounds are actually pretty decent, and you cannot really improve them. Okay, so that's why we call them tight bounds. But if alpha is much smaller, which is what you sometimes care about, then so what that means is that, let's say I want alpha to be 0.00001, right? So sometimes you want this confidence to be really really high. Okay, like imagine you're trying to estimate some parameter and you want the failure probability of this estimation to be super low, right? And like the textbook gives this example of like something to do with the Challenger spacecraft. And there are critical situations when you want a very very high confidence in your estimators. Okay, so in those cases, turns out Chebyshev does not give you great bounds. So let's see how to get bounds over there. Okay, and so the main theorem that we will use for that, again, we are not going to be able to prove this theorem. This is beyond the scope of this course, but I would like to state it, is what is called the central limit theorem. Okay, and I'm going to state it for now for the Gaussian distribution. Okay, and what is this theorem state? Okay, so what is the statement of this theorem? So suppose x1, x2 up to xn are distributed as or are drawn from, okay, let me just say distributed as n of mu sigma squared. Okay, so these are all Gaussian. Okay, that's why I'm saying this is for Gaussian. Then the random variable, then also let's define a name for it. Okay, so let t be the empirical mean. Okay, then t minus mu divided by sigma by root n. Okay, let me write it in this form and then I will explain it. Okay, so this is a random variable, okay, is distributed as a Gaussian n01. Okay, so this is a very strong statement, right? So what this is saying is that if you look at this complicated random variable, which is t minus mu divided by sigma by root n, this is actually, we know exactly what this distribution is, and its distribution is a Gaussian whose mean is 0 and variance is 1. Okay, and and note that this is totally non-obvious, right? So it's telling you that if I have n variables that are distributed as Gaussian, I compute the empirical mean, okay, empirical mean of these guys. That's a random variable t. That guy has some distribution which for now, which a priori is not clear. Then it's saying that t minus mu divided by this quantity sigma by root n is distributed as a Gaussian, which is n01. Okay, and this is equivalent to saying that t is distributed as a Gaussian with mean mu and variance sigma squared divided by n. Okay, so that's the square of this denominator. Okay, and this is you can imagine that this would, I mean, if I were to tell you what, if I were to ask what the mean of t is, we already saw that t is an unbiased estimator, therefore its mean is mu. If I were to ask you what its variance is, we know that from what we saw before, t expected value of t minus mu whole squared is sigma squared by n. So I know that its variance is sigma squared by n. But what the central mean limit theorem is telling us is that it's not just some distribution with mean mu and variance sigma squared by n, it is actually a Gaussian distribution with mean mu and variance sigma squared by n. Okay? And that's a very strong statement. Okay? Now it turns out that this is true not just for, so the main statement of the central limit theorem more generally is that when n tends to infinity, okay, so the above statement is true not just for Gaussians but for xi that are drawn from D for any distribution D with mean mu and variance sigma squared. Okay, so this is like so this is called the central limit theorem, and the proof of this is well beyond the scope of the class. I mean, it requires, it's not very difficult, but it requires a lot of effort. And basically what this, but the statement is actually very important to understand, right? So what it's saying is that, so these are xi, I going from 1 through n. Okay, so what this is saying is that if I take lots of samples x1 through xn from any distribution that has mu and variance sigma squared, okay, then, and I were to construct this new this new estimator, which is like t minus mu divided by sigma by root n. Okay, if I were to look at this quantity, this is of course a random variable, t minus mu divided by sigma by root n. This is some random variable. Okay, then this random variable, its distribution is exactly like a Gaussian. Okay, this distribution is the Gaussian distribution. So no matter what you start with, so D can be anything you want, and but you take lots of samples. Okay, so t minus and you construct the empirical average, and you look at t minus mu divided by sigma by root n, then the distribution of this quantity is exactly as a Gaussian with mean 0 and variance 1. Okay, and this is a very powerful statement, and yeah, so we'll see, and it's important to note that this is true only in the limit, right? So there are lots of theorems known about like trying to quantify, like how large should n be so that you get that this quantity is very close to a Gaussian and things like this. There's a lot of research on that. Okay, but yeah, so we will use this theorem in the next lecture, but only for the Gaussian for now. Okay, so all right, let's stop here.